Because good day viewers, and welcome to part 3 of this redox reactions video series. In case you missed part 1 and 2, a link of part 1 and part 2 is provided in the description below. So in this situation, we are going to look at examples of calculating oxidation numbers. We are to calculate the oxidation numbers of the following species, and then we give their IUPAC nomenclature. So let's look at these examples. Here we're going to calculate the oxidation number of chromium, here oxidation number of sulfur, here manganese, and then here for the phosphorus, chromium, and manganese here. So we begin with the first example. Of course, this is a neutral compound, and we said the algebraic sum of the oxidation numbers of atoms in a neutral compound is equal to 0. So this means we say K2Cr2O7, we are going to assign oxidation numbers. The oxidation number of oxygen is -2, that of potassium +1, and chromium we don't know, we say X. So working this out, the potassium here, we have 2 atoms, so it's going to be 2K. Here we say 2Cr plus 7 oxygen, everything will be 0. So this will give us 2 into +1 plus 2 into X plus 7 into -2, everything will be 0. So this will give us 2 here plus 2X, and this will give us -14 is equal to 0. So +2 minus 14 gives us -12. So 2x minus 12 is equal to 0. We can transpose this. So 2x will be equal to 12. And the value of x will be +6. So this one we can refer to it as potassium heptaoxodichromate 6. That is the IUPAC nomenclature of this species. And then we look at the second example. We have H2SO4. Here also we assign oxidation numbers. Oxygen is -2, hydrogen is +1, sulfur is Y, we don't know. So this is a neutral compound. So the algebraic sum of the oxidation numbers of the species in there is going to be 0. So we have 2 hydrogen plus sulfur plus 4 multiplied by oxygen, everything will be 0. So hydrogen is +1, 2 by +1, sulfur is Y, +4 into oxygen is -2, everything 0. So this will give us here +2 plus Y -8 is equal to 0. +2 minus 8 here gives us -6. So we have Y -6 is equal to 0. So Y will be equal to +6. So we can refer to this as tetraoxosulfate 6 acid. We cannot say hydrogen tetraoxosulfate 6, okay? For the IUPAC nomenclature, we say tetraoxosulfate 6 acid. We go to example 3. We have the KMnO4. This is also a neutral compound, so the algebraic sum of the oxidation numbers is going to be 0. So here oxygen is -2, manganese, you say X, potassium is +1. So if we work this one out, it means potassium plus manganese plus 4 times oxygen, everything will be equal to 0. So here potassium is +1, manganese is X, +4 into -2, everything will be equal to 0. So we get 1 plus X. This gives us -8 is equal to 0. +1 minus 8 is -7. So X minus 7 is equal to 0. X is equal to +7. So we can refer to this as potassium tetraoxomanganate 7. So that is for this. And then we look at the fourth example. The fourth example we have here is PO4 3-. So PO4 3-, we assign oxidation numbers. So we have here PO4 3-. So here we can say phosphorus plus 4 multiplied by oxygen, everything is equal to -3. Why did we equate to -3? We equate to minus 3 because we learned from the rules in part 2 that the sum of the oxidation numbers of species in a polyatomic ion is equal to the charge, and the charge we have here is minus 3. So that's the reason we equated it to minus 3. So this means it is going to be X, which is the oxidation number of the phosphorus, plus 4 into negative 2 is equal to negative 3. So this will give us negative 8 is equal to negative 3. We transpose this. So X will be equal to negative 3 plus 8. X will give us plus 5. So we can refer to this as tetraoxophosphate 5. And then we look at the fifth example. The fifth example, we have Cr2O7 to minus. With Cr2O7 to minus, we assign oxidation numbers. Oxygen is minus 2, chromium is X. We work it out. Here we have 2 atoms of chromium, so we say 2Cr plus 7 atoms of oxygen. 7 multiplied by this, we equate it to the charge because it's a polyatomic ion. So the oxidation number of chromium is X plus the oxidation number of oxygen is minus 2 is equal to this. So 2X minus 14 is equal to negative 2. So 2X is equal to, if we transpose this, we get minus 2 plus 14. So 2X will give us positive 12. Making X the subject, we have it to be plus 6. So we can refer to the species as a heptaoxodichromate 6 ion. Okay. And then finally, the sixth example, we have here MnO4 minus. So like we did for the previous examples, we assign oxidation numbers as well. Oxidation number of oxygen minus 2, manganese, that is X. So working this one out, we have only an atom of manganese here. So we say Mn plus 4 atoms of oxygen, and we equate to the charge of minus 1 because it's a polyatomic ion. So the oxidation number of manganese is X plus 4 into negative 2 is equal to negative 1. Plus times minus is minus. 4 by 2 is 8 is equal to minus 1. X will be equal to minus 1 plus 8. X will be equal to plus 7. So we can refer to this as the tetraoxomanganate 7 ion. Okay. So this is the concept of oxidation numbers calculation. Next, we learned earlier that when you have oxidation taking place in a particular reaction, reduction will also take place. So that tells us that oxidation and reduction are simultaneous processes. They are complementary processes. If oxidation takes place, then reduction will surely take place. Any particular chemical process wherein species undergo a change in the oxidation numbers, we refer to it as a redox reaction. So let's look at some types of redox reactions. Under the types of redox reactions, the first one we are going to look at is addition reaction. In an addition reaction, you have a species reacting with another species to give you a single product. So we have here A that will react with B to give us AB. So a practical example of this can be, let's say for example, we have gaseous hydrogen reacting with oxygen, and when these two are sparked, you have water that comes out of it. So if we want to balance this equation, we can place 2 here and replace 2 here. This is a redox reaction. Why did we say it's a redox? Hydrogen in its free state 0, oxygen in its free state, oxidation number 0. We've just looked at it. And oxygen here minus 2, hydrogen plus 1. So we found out that what hydrogen is increasing in charge and oxygen is decreasing in charge. So that tells us hydrogen is oxidizing by losing electrons and oxygen is reducing by gaining electrons. So we can write the oxidation half and reduction half. The oxidation simply means here 2 moles of gaseous hydrogen is becoming 4 moles of hydrogen ions after losing 4 electrons. And this simply means here for the reduction, It means oxygen molecule, each atom of it gains 2 electrons. So 2 atoms means 4 electrons to be gained to give us 2 oxide ions. So we can add this together, cancel this, and we work it out. So we get 2H2 plus oxygen to give us 4 hydrogen ions and 2 oxide ions. So it can be further simplified as 2 hydrogen molecules plus a molecule of oxygen to give us 2 moles of water. So this is a practical example of a redox reaction. But not all addition reactions are redox reactions. A typical example is dissolving sulfur 4 oxide gas in water. If we dissolve sulfur 4 oxide gas in water, we are going to produce a very weak acid called sulfurous acid, which has a very low concentration of the sulfurous acid in the water. So this here is the example. Sulfur 4 oxide gas being dissolved in water to give us sulfurous acid. We call it the trioxosulfate 4. So why did we say this reaction is a non-redox reaction? Mind you, I told you earlier, I said in any chemical process wherein you have the oxidation numbers changing, that tells you that particular chemical process is a redox process. So here, oxygen has oxidation number -2, sulfur has oxidation number here +4. Oxygen here -2, hydrogen here +1. Oxygen here -2, hydrogen here +1. 3 by this is -6. -6 plus 2 is -4. You transpose it over, it becomes +4. So if we check here, there is no change in oxidation numbers. No change in oxidation numbers. So that tells you this is a non-redox reaction, whilst this other addition reaction is a redox reaction, but this one is a non-redox reaction. Okay, so not all addition reactions are redox reactions. The next we are going to look at is decomposition reactions. In a decomposition reaction, you have a single species, let's say for example AB, decomposing into A plus B. So you can have 2 products or 2 or more products being formed from a single species. So let's say here we have water molecule, liquid, being decomposed into gaseous hydrogen and oxygen gas. This reaction is a redox reaction. Oxygen here has a charge of -2, hydrogen has a charge of +1, hydrogen here in its free state is 0, and oxygen here 0. So you find out that what? The oxygen here is increasing, okay, from -2 to 0, and the hydrogen here is decreasing from +1 to 0. So that tells you this is oxidation and this one is reduction. So this is an example of a redox reaction. The third type of redox reaction we're going to look at is a combustion reaction. For the combustion reaction, of course, combustion means burning. Let's say here we want to look at the burning of methane gas with oxygen. So when you have a hydrocarbon burning in oxygen, 2 products are formed as carbon dioxide and water. So here we want to know if this is a redox reaction. Hydrogen gets a charge of +1, and this carbon is going to get a charge of -4. Oxygen here in its free state is 0. Oxygen here in the combined state -2. So this carbon is going to get +4. Hydrogen here is +1, and oxygen here -2. So you find out that what? The oxidation number of hydrogen does not change. So meaning it is a spectator. Carbon here from -4 to +4, that tells you it's an increase. It is oxidation. And oxygen from 0 to -2 and -2. So that tells you it is decrease. That means it is reduction. Okay. So combustion reactions are examples of redox reaction. The fourth one we are going to look at is a displacement reaction. In a displacement reaction, of course, we have single displacement and double displacement. The single displacement is a redox, and most double displacement are not redox. For single displacement, let's say we have A reacting with BC. So what happened? A is going to displace B and react with AC. So you have AC that is formed, and then B is set loose, set free. So let's look at an actual example of what we've just demonstrated here. Let's say sodium solid reacting with hydrogen chloride aqueous, which is hydrochloric acid. So what happens? Sodium is going to displace this hydrogen and give us sodium chloride aqueous, and then you have hydrogen gas that is released. Okay. So in this situation, we want to know if this is a redox reaction. And we said the charges have to change. So here in its free state, sodium is 0, hydrogen gas 0 in the free state. Hydrogen here +1, chlorine here -1, sodium here is +1, chlorine here -1. So you find out that what? The oxidation number of chlorine does not change. So chlorine is serving as a spectator ion there. But you find out that sodium increased from 0 to +1. So that tells you oxidation is taking place, and hydrogen decreases from +1 to 0. That tells us reduction took place. So this is an example of a redox reaction. Okay. And let's look for the double displacement. So let's say here we have AB reacting with CD. What happened? A displaces C to react with D, and then B then combines with C, giving us BC. So let's look at a real life example of what we've just demonstrated here. Let's say we have iron rust, Fe2O3 reacting with hydrochloric acid. So what is going to happen in this case? Iron is going to displace hydrogen and react with chlorine, giving us iron trichloride. And then this remaining oxygen is going to react with the hydrogen to produce water. So we want to see if this double displacement is a redox reaction. Here, iron has charge of +3, oxygen has charge -2, chlorine here -1, hydrogen here +1, chlorine here -1, iron here is +3, oxygen -2, hydrogen +1. So if you check here, there is no change. Iron +3, +3, oxygen -2, -2, hydrogen +1, +1, chlorine -1, -1. So this is an example of a non-redox reaction. Okay. And finally, for the types of redox reaction, we look at the fifth example, referred to as a disproportionation reaction. Disproportionation reaction, you have the same species that simultaneously oxidizes and reduces. Let's say here we want to look at hydrogen peroxide aqueous. This species is going to simultaneously oxidize and reduce, because this one here can break into water and oxygen gas. So this is an example of it. So here, what happens? Oxygen has a charge of -1 and hydrogen has a charge of +1. Hydrogen here +1, oxygen here -2, and here oxygen here is 0. So you find out that what? In this reaction, oxygen increases in oxidation number. So that tells us here it is oxidation that is taking place. Okay? And here, this same oxygen again decreased in oxidation numbers. So that tells us in this case it is reduction that is taking place. So the oxygen in the hydrogen peroxide is being simultaneously oxidized and reduced. So this kind of reaction, we call them disproportionation reaction, wherein you have the same species simultaneously oxidizing and reducing. Let's say this is our first example. Let's look at another example, that is reacting chlorine with sodium hydroxide, an alkali. So when you react chlorine and sodium hydroxide, you are going to get sodium chloride, sodium oxochlorate, and then you get water. So if we want to balance this, we can place 2 in front of this. Okay, placing 2 here, chlorine here is 2, 1 chlorine, 1 chlorine, chlorine is 2, and then sodium 2, 1 sodium, 1 sodium, oxygen 2, 1 oxygen, 1 oxygen, hydrogen is 2, and then you have 2 hydrogens here. So let's assign the oxidation numbers here and see. Chlorine in its free state is 0, sodium here +1, hydrogen +1, oxygen -2. Sodium here +1, oxygen here -2. Now, in this case, chlorine is least electronegative than oxygen. So we said the least electronegative species will have an oxidation number that is positive. So chlorine is going to get oxidation number +1 instead of -1. Oxygen here -2, hydrogen here +1. So now if you observe, you will find out that chlorine molecule here increased in oxidation number in the sodium oxochlorate. This is sodium oxochlorate. Okay, so here it increases from 0 to +1. So that tells us in this case it is oxidation that took place. Oxidation took place here, and then the same chlorine again is reducing in oxidation number. Okay, that is in the formation of the sodium chloride. So here the increase was from 0 to +1. Here the decrease is from 0 to -1. So because it is decreasing, that tells us it is reduction. So this is also an example of a disproportionation reaction. You have the same species simultaneously oxidizing and also reducing. It oxidizes in the formation of the sodium oxochlorate, and it reduced in the formation of the sodium chloride. So these are examples of redox reactions. So next we move over to non-redox reactions.